In this video, we'll be discussing exclusively Raman effect, and here I would like to introduce you with the classical and quantum mechanical understanding of this Raman effect. Now, the classical theory of the Raman effect is basically based upon polarizability of the molecule, which reflects how easy an electron cloud of a molecule can be distorted by an external field. Now, this external field, taking into account the electromagnetic radiation, where the electric field has large magnitude. The technique is based on the molecular deformations in the electric field that's determined by the molecular polarizability. And if we talk about the laser beam can be considered as an oscillating electromagnetic wave with a vector, with an electric field vector interacting. Upon interaction with the sample, what it does, it induces the dipole moment, and 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 this is what deforms the molecule. Now, because of this periodical deformation, what happens here is that the molecule starts vibrating. It starts vibrating with some characteristic frequency. And the scattered light that's obtained, the scattered light can have frequency equal to that of the incident radiation, and it can have the frequency less than that of the incident radiation, and it can be more than that of the incident radiation. Now, if the scattered electromagnetic radiation has the same energy uh, as that of the initial radiation, then this is what is called as Rayleigh scattering. And if the scattered electromagnetic radiation has the energy, or I can say has the frequency less than that of the incident radiation, we call it anti-Stokes. We call it Stokes. And if the scattered radiation has more frequency, we call them anti-Stokes. Now, if we think about the same problem in terms of the quantum theory, and in quantum theory, the magnitude of the Raman effect, it basically correlates with this physical quantity known as polarizability of the electrons in a molecule. It's a form of inelastic light scattering, but a photon excites the sample, and this excitation puts molecule into some, I should call it, into some virtual energy state for a very short period of time. Now, before this photon is emitted in an inelastic scattering, if there is an inelastic scattering, means that the energy of the emitted photon is of either lower energy, or it has the energy greater than that of the incident energy that it possesses. Now, after the scattering event, what happens is that the sample is in a different rotational or vibrational state. And for the total energy of the system to remain constant after the molecule moves to a new rotational or vibrational state. We may also call it moves to a new Rovibronic state. The scattered photon shifts to a different energy, and we can say here, and therefore a different frequency. This energy difference that we have between the incident photon and the scattered photon, it's equal to that between. It's basically the difference between the initial and the final Rovibronic states, or I should call it rotational and vibrational states of the molecule. Now, if the final state is in higher energy than that of the initial state, the scattered photon will be shifted to a lower frequency. Lower frequency means lower energy, so that the total energy of the sample remains the same. Now, this shift is what's called as Stokes shift. It may also be called as downshift. And And if the final state is lower in energy, the scattered photon will be shifted to a higher frequency. And it is, this is what is called as anti-Stokes shift. Or it may also be called as upshift. Now, for a molecule to exhibit, for a molecule to exhibit a Raman effect, there must be a change in its electric dipole and electric dipole polarizability with respect to the vibrational coordinates that correspond to this rovibronic state. The intensity of the Raman scattering, if you take into account the intensity of the scattered photons, this intensity of the Raman scattering is proportional to this polarizability change. Therefore, the Raman spectrum, and what is this Raman spectrum? It is basically the scattering intensity that we have as a function of the shift in frequency. And what it does, this Raman spectrum, it depends on these rotational and vibrational states of the molecule. The Raman effect is based on the interaction. It has a basis in the interaction between the electron cloud of the sample and the external electric field of the monochromatic light. And this is which can create an induced dipole moment with a molecule, and when there is induced dipole moment with the molecule based on its polarization. So, dear students and dear friends, let's try to talk about Raman scattering, and in this topic, let's start with the vector potential, and and what is important here is that we will try to develop the quantum theoretical approach of inelastic scattering of light, and we will try to lay down the foundation of how the electromagnetic fields interact with the matter, and then we will try to analyze this Raman scattering. So let's write down the vector potential. The vector potential A. Okay, so as a function of r, so it's a vector, and this is the vector potential of the electromagnetic field, and we can write down this vector potential as an ensemble of oscillators, as A of r is sigma 2 pi c square h cross by v omega as a function of, say, some eta, and whole raised power 1 by 2, and then we will have the creation and annihilation operators, say a lambda plus a lambda dagger, and use some polarization vector E cap as a function of this eta and lambda, and e to the power of I eta dot r. So in this equation, this is a very crazy equation, and we can see that we have this a dagger and a lambda dagger. They are the creation, and this is the creation operator, and this is the annihilation operator, and the annihilation operator for the photons, and choosing this eta to be the wave vector here. Wave vector. And the lambda that's being used here is used for polarization, and the unit polarization E cap as a function of eta and lambda, and the frequency as a function of this k, and this v is the volume. And this equation has been established by Boehm in 1969. And for cubic and optically isotropic crystals, this electromagnetic wave will be purely transverse. It will be purely transverse. So if it is transverse, then this eta, generally we use k for it. So eta dot e cap as a function of eta and lambda, this must be equal to 0. And from this, what follows is that the divergence of this vector potential is equal to 0, which is basically the Coulomb gauge. So we are assuming a Coulomb gauge here. And if we have to write down the Hamiltonian, if we write down the Hamiltonian for this interaction between the electromagnetic radiation and the matter, and let us write down the Hamiltonian as P minus E by C A as a function of R and T whole square divided by 2m. So this is our kinetic energy term, and then we will have the potential energy term if I use E and use phi as a potential as a function of R and T, and then V of R of T. So this is our Hamiltonian, and this Hamiltonian is a representative of the interaction between the electromagnetic radiation and the matter. Now, this VR of T, what it describes here is that this VR of T describes all other potentials that are seen by the electron. And this equation that we have here, we can write down this equation in a very convenient way, and we can break down this equation into H0, H1, and H2. And we have already discussed this kind of interaction when we talked about absorption, emission, and spontaneous emission of radiation in terms of a single electron atom. Now, here, this H0 is a representative of, say, psi dagger of R and P squared by 2m and plus V R of T and psi of R. So I think I should enclose it in some D3R over this volume. So this is our ideal Hamiltonian when there is no interaction of the electromagnetic radiation with the matter. And then we have the first correction as H1, and that is to be given as psi dagger of R and E by 2, it's not 2, E by MC. And then we have P dot A, and A is the function of R and psi of R. Using a different notation here in this problem, trying to discuss this. And then we have H2. This H2 is psi dagger of R, then E square by 2m C square A of R dot A of R psi of R. Where we have here this psi dagger and psi dagger of R and psi of R, they are basically the representatives of electron field operators. They represent the electron field operators, and we can write down these operators as say psi of R is a sigma Ci of say K sigma I K sigma, and psi dagger of R is sigma Ci dagger and K sigma times K I and K sigma. And what we have here is that this C dagger, C dagger and C, they are again the creation and annihilation operators for conduction electrons. I think it will be more precise because I have been using B dagger for electrons. So let me use dagger, bi dagger, and b. So this bi dagger is they are the creation. This is the creation operator for the conduction electrons or holes, and Bi is the annihilation operator for conduction electrons or holes, and this H1 that we have here, this H1, it really plays an important role because it has a contribution to the interband electron scattering. While looking for this H2 term, this H2 is dominant. It's the dominant contribution for intra-band electron scattering, and H1 is it is linear in photon creation and destruction operators, and its contribution to scattering comes out in second order, and the matrix element for this H1, what it does basically is it allows the scattering in which we have some initial and final electronic states. So you have some initial, say these are initial and final electronic states, and so I should say here, therefore, this H1 term makes important contributions to the kind of excitations that are considered, and it's the important element when computing some differential scattering cross section from phonons. And what are these phonons? These phonons are the quantized acoustical waves that may be present in these maybe solids, as and in case of liquids. So what is important here to develop is an expression for this, what we call as differential scattering cross section, and certainly the transition probability between some initial state, if we have some ket of some initial state as a ket of 0 and some final state as a ket of, say, f. And we can write this kind of transition using Fermi golden rule. And what is that? That's this transition probability is 2 pi by h cross. Then choose a sigma for this final state is f, and we have the interaction Hamiltonian here, and we have the initial state 0, and we have to take the square of this matrix element, and then we have del of EF minus h cross omega s minus E naught and minus h cross omega I. And we can think of this matrix element that we have here, and this matrix element can be labeled to what is called as T matrix. What's called as T matrix. Now, what is this T matrix? In the T matrix method, the incident and the scattered. Suppose we have the incident, we have the incident and scattered fields. These fields are expanded in series of some suitable vector spherical wave functions, and the relation between the columns of the respective expansion coefficients is established by means of this what we call this as transition matrix, or we call this as T matrix. And this concept of T matrix can be applied to entire scatterer as well as to separate parts of the composite scatterer that we have. So proceeding from here, we'd like to write down this transition probability as 2 pi by h cross sigma, and if then we'll use this T, that's transition matrix whole square, and then we will have this delta function of EF minus H cross omega S minus E naught minus H cross omega I. And where this matrix element that we have here in terms of the interaction Hamiltonian is labeled as the T matrix, and the light scattering efficiency can now be calculated. We can calculate this scattering efficiency of the light using this T matrix. And what is important here is that the number of scattered photon states, if we directly write down the number of scattered photon states in a solid, say. So when we talk about solid, we have a solid angle d omega, and we have a frequency interval. We have a frequency interval d dw, and this number of scattered photon states in a solid can write down as n of p equal to v upon 8 pi cube omega s square by c cube d omega and d omega. Now, the number of transitions that we have, the number of transitions per unit time, per unit solid angle that we have per unit frequency interval, we can find that by multiplying this number with this W in a form that we can think of writing that as NP of. So I'm using NP here as a number of this W divided by d omega d solid angle. And finally, what we're going to obtain from here is the differential scattering cross section. And this scattering cross section can be obtained, and this scattering cross section can be we can write down this scattering cross section in a mathematical form as d2 sigma by d omega d solid angle is v square omega s square by 4 pi square across c to the power of 4 n I, and then sigma, then we have the matrix element, that's if H interaction and 0, and this is whole square, and then we have the delta of EF plus H cross omega S minus E naught minus H cross omega 1. Now, the point of interest over here is that the calculation of this differential cross section, this differential scattering cross section, can be melted down to calculating the T matrix for the desired excitations that can be there by virtue of the interaction of the electromagnetic interactions with the material particles, and we can think in terms of the general Feynman diagrams, and what we have here is that we have the incident photon. Suppose this is an incident photon. Let me call this as incident. This is incident photon, and what it does, it interacts with the matter. So it has an interaction with the matter, and while interacting, what it does, it produces the electron-hole pair. So we have electron-hole pair, and this electron-hole pair is then scattered. It is scattered by some elementary excitations, and having this scattered elementary excitations, and again what we have is is we have the de-excitation stage where we this electron hole pair it recombines, and it recombines after emitting a photon. Now the interactions are understood to be instantaneous. So what we have is we have He. I'll call this Hee. I'll call this HER, and this is HER. So things are purely arbitrary here. Now, the interactions that we have here, these interactions are instantaneous, so that the order of the interaction can be interchanged. And talking about this diagram, what we have here is this HEE is the Hamiltonian for the interaction of uh, electron electron or hole with some elementary excitations. This HER this HER, they are incident and these scattered photons respectively. So this is HER for some incident state, say this is I, and this is HER for some scattered state, and that is IS. So what I said before is that these interactions that we have here, they happen to be instantaneous, and when they happen to be instantaneous, then the order of the interaction can be changed, and the matrix for this general scattering process, the T matrix for this general scattering process, can be written down. And what will be that? This T can be written as sigma I1. This I1 and I2, they are the intermediate states. So we have incident radiation interacting, and then there are, say, some intermediate states that are occurring, and then there is the emission of the photon. So we can write down this as the matrix of HER, and then to I1. Okay, so I1 and then HER, then another state I2, then I2 as the final state, and HEE, electron hole pair, and the ground state. This whole thing is divided by E naught minus E1 minus H cross omega 1 minus H cross omega EE times E naught minus E2 minus H cross omega 1. Then plus, we have F, then HER, then I1, and then we have another matrix element, I1, HEE, and then we have I2. Okay, and then we have I2 HER and 0. Whole divide by the same denominator, E naught minus E1 minus H cross omega I minus H cross omega EE, closing then E naught minus E2 minus H cross omega 1, and then plus what we have, this is F, and we start with HEE here, the matrix element of HEE, then we have R1, and then what we have is R1, HER, and I2, and then I2, HER, and the 0 state. Divide by E naught minus E1 minus H cross omega I minus H cross omega EE times E naught minus E2 minus H cross omega I. So what we have here is that this HER and this HEE, this HEE is the interaction Hamiltonian between the electron and some specific elementary excitation of interest, depending on the interest of the situation, that what kind of interaction is taking place. And these E naughts, like E naught, E1, and E2, these are the energies of the initial and two intermediate states, and this H cross omega 1 and H cross omega EE, they are the energies of the incident light wave, and the and the excitations involved, and the excitations involved in the process. So this is the T matrix for this kind of interaction. And talking about the scattering from here and boiling down this crazy thing that's on the paper, and what we have is the phonon scattering. I mean, as I said, the phonons are basically quantized acoustical waves. The phonon scattering process is basically, we can represent this by looking for the diagram. We can draw a diagram for it. I mean, we have the incident photon, and then this incident photon has some frequency, and what it does, it creates electron. We have the incident photon. It creates electron and hole pairs, which in turn is scattered via electron phonon interaction by emitting or absorbing a phonon of frequency, say omega p. This omega p. So finally, the electron and hole pair, subsequently, what happens to them? They pair up again, and they recombine by emitting a photon of energy omega s. They emit the photon of energy omega s. Now the T matrix can basically be it can be read off from the equations that we have written down here, and by simply replacing this HEE that we have with HEP, the electron phonon coupling Hamiltonian, and HER with H1, and then we will have the important electron radiation coupling term for phonons, and we can think of writing down those crazy equations in terms of phonons. The T matrix for this will be T is sigma I1, I2, that is F, and replacing this by H1 and I1, and then I1, H1, and I2, and then I2, H electron phonon as the ground state 0, divide by E naught minus E1 minus H cross omega I minus H cross omega pH. And using phonons, this is E naught minus E2 and minus H cross omega I. Then plus F of H1, then I1 closing, then I1 H electron phonon, and then I2, then I2 H1, and divide by the same thing, that is E naught minus E1 minus H cross omega I minus H cross omega phonon times E naught minus E2 minus H cross omega I. And then the third term will be F of H electron phonon, and then we will have I1, and then we'll have I1 H1 and I2, then we'll have I2 and H1 and 0. Whole divide by the same denominator, E naught minus E1 minus H cross omega I minus H cross omega phonon times E naught minus E2 minus h cross omega I. And and this is what shows us we have here the phonon. We're trying to write down this T matrix in terms of scattering of phonons, and we can think of putting it in some systematic diagrammatic way. I mean, what we have is we have some states as, and we have K, and what we have is we have the interacting photon, and we have the transition, and this transition may lead like this and like this, and 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 we will have some omega I, and we will have some scattered omega S, and we will have some omega phonon. So what am I trying to tell here is that what this diagram represents is that we have the light scattering by the optical phonons, wherein the electron hole pair is created. There is a creation of electron hole pair by the absorption of this incident photon. We have the incident photon; it creates electron and hole, and and then the electron or the hole is scattered in the emission or the absorption of a phonon, and finally this electron hole pair recombines and emitting a photon of frequency omega s. And this is basically a representative of the Feynman diagrams, representing the phonon scattering process, where at every vertex the light interacts with the electron, and there is one electron phonon interaction involved in it.